Good morning, everyone. It's a great honor for me to be with you today online as a keynote speaker in this important session on water management and resource efficiency. My presentation will focus on a critical challenge such as agricultural water management and whether it can adapt to climate change. I will discuss this through the perspective of the soil, water, energy nexus, with a special emphasis in olive cultivation. Also based on successful examples in different regions, I will try to show how integrated strategies can enhance both resilience and sustainability in olive cultivation. So, just a moment. In order to go in another slide. Sorry to stop share and repeat this process because I cannot go to the next slide. Now, sorry for this. Yeah. Can you see only the first slide? I don't know why I will not go to the next one. Sorry for this. Okay. So you can see the second slide here. Here, the first, the second slide is okay. Yes, I can hear you. So here, now you can see. Okay. Sorry for this. All right. Okay. Now, agriculture is fundamentally dependent on water, both in terms of availability and quality. As you know, without sufficient water, crop yields decline, and global food security is directly threatened. At the same time, climate change affects the hydrological cycle, making water resources less predictable and reliable. This, of course, raises a central question: how can agricultural water management adapt to ensure both food security and sustainability under climate complexity? So this question is the focus of my talk today. In this slide, we can briefly see the impacts of climate change on water and agriculture. The first crucial impact is the increased irrigation demand, mainly due to higher temperatures. Another impact is the declining of water quality from runoff, erosion, and pollution, a fact that can reduce the usability of surface and groundwater resources. Extreme weather events, such as droughts and floods, are becoming more frequent and severe. Another effect is related to the reduction of yields and land use shifts. And finally, coastal regions in many cases face salinization from rising sea levels and, of course, saltwater intrusion. These challenges together threaten the sustainability of agricultural system, especially in water-sensitive crops such as olives. To address these challenges, we need a wide range of adaptation strategies. These strategies can be separated into 10 different categories, as we can see in this slide. So these strategies include, for example, infrastructure measures such as floodplain and drainage management, and the creation of small-scale reservoirs. They also involve ecological approaches like restoring wetlands and crop biodiversity enhancement. In addition, water reuse and recycling are becoming increasingly important for irrigation purposes, especially for the areas that faces problems with water availability. Another point is the agricultural insurance to protect farmers from economic risk. Equally vital are soil and water conservation practices to maintain soil moisture and fertility. In addition to those adaptation strategies, the development of climate resilient crops, smart irrigation technologies, and appropriate water allocation policies to ensure a fair distribution of water resources are also of great importance. Together, these strategies highlight that the adaptation is not a single solution, and these strategies should be selected based on the level of implementation. For example, some actions work better at the national or region scale, while others are more effective at the farm level. Also, we need to look at the balance between cost and benefits, making sure that the money and effort invested are worth the results. Based on this, we must act quickly. Climate change is already creating serious risk, so we cannot afford to delay. This means we need integrated solutions that fit local conditions and involve the people directly affected. At the same time, research must combine technology, field data, and of course, good agricultural practices. Agriculture must not only adapt, but also become more sustainable and resilient under what we call climate complexity. And this means more frequent and intense extreme events and indirect effects such as soil erosion, pest infestations, and increased energy demands. These combined impacts make our agricultural system far more unpredictable. So in this context, the soil, water, crop, and energy nexus can offer a useful framework, creating farming systems that are more adaptive while maintaining both productivity and sustainability. The key question also is how can such integrated approaches transform agricultural system to face this new reality? Let us now look more closely at this nexus, starting with soil and water. Healthy soils are not simple chemical media, but living systems, as you know. When soils are managed properly, they can buffer climate extremes, retain water, and resist erosion. As you know, practices such as cover crops, reduced tillage, and compost application can increase resilience of the farms. On the water side, agriculture is the largest consumer of global fresh water, and this raises issues like who controls water, how it is allocated, and how it is monitored. Of course, tools such as precision irrigation, deficit irrigation, and digital monitoring can optimize water use and help both farmers and local authorities to protect their water supplies. Crop management is another vital element of the Nexus. Farmers need varieties that can tolerate, for example, on drought and salinity. Crop rotations and mixed systems help reduce both climate and market risk. In addition, organic farming and agroecology can improve soil carbon, water retention, and reduce chemicals inputs. But we must also be realistic, as not all these systems guarantee stable yields or income everywhere. About the energy, energy is also a critical component. Agriculture requires energy for irrigation, pumping, fertilizer production, and post-harvest operations. At the same time, climate variability affects energy supply, making systems more vulnerable. Renewable energy sources, such as solar or biogas, are of course promising, but yet without regulation, cheap renewable energy can create extra problems, such as the over extraction of groundwater, and this is another issue that we will see. Now, let me now turn to some successful olive-related examples of the Nexus in action. In Morocco, which is a semi-arid region suffering from scarce water, high energy cost, and inefficient irrigation. Farmers traditionally use diesel pumps for irrigation, which are expensive and polluting. So, in this case, the intervention combines two actions, replacing diesel pumps with solar energy and installing drip irrigation systems. This not only saves energy, but also delivers water directly to the olive parcels. The results were impressive. Olive yields improved, water savings reached up to 60%, fuel cost dropped, and carbon dioxide emissions were significantly reduced. So based on this approach, approximately over 100,000 hectares of farmland were revitalized, demonstrating, of course, that the powerful synergy, the powerful synergy of water and energy solutions. Here we can see a schematic representation of this system. The system has been designed with two pumps. One to draw water from groundwater and pump it into a reservoir, and the second pump is used to pump water from the reservoir to the olive crops. On the left part of this slide, we can see the real photo of this infrastructure. A second and more detailed example comes from Crete, where olive groves often face inefficient irrigation and farming practices. Here the solution was the application of good agricultural practices related to water and soil, as well as a three-level advisory scheme for proper irrigation. Let's see some more details for each of these two interventions. Regarding the application of good agricultural practices in Crete olive farms, here we have 5 different goals. The first goal was to reduce water losses by evaporation by applying pruning and weed residues on the soil, creating a protective layer on the soil in order to reduce evaporation from the ground. In order to reduce water loss by transpiration, this was achieved by spring wheat management, by winter and summer pruning and application of kaolin, which is sprayed on the tree canopy, and it has proved to reduce and protect at the same time the olive trees from for pests such as ducks. Now, in order to reduce water losses by the deep infiltration, this was achieved by increasing soil organic matter and using fertigation, which means use of fertilizers through irrigation. Another goal was, of course, the proper agricultural to include rational use of irrigation, water and fertilizers, and application of deficit irrigation. More information about this we will see in the next slide. Finally, reducing water losses from runoff related practices are to maintain weeds during winter, no soil tillage, and legumes sowing. And especially in slopy areas, natural barriers were introduced in order to prevent water from runoff and to reduce water erosion. This last practice is demonstrated in detail to this slide by some photos. So these barriers were strategically located vertically to the flow and can be made from natural materials such as stones, which are held together by olive nets. Here we can see this point. In order to evaluate the efficiency of this practice, we had constructed water traps at the downstream part of slopy olive parcels in order to measure the amount of water collected. And of course, our aim was to have less water collected in demonstration olives parcels compared to the control olive parcels where there are no barriers, which of course was validated based on our results. Now, regarding the three-level advisory scheme for proper irrigation. This scheme has three different levels of implementation, depending on the spatial level and the end user's needs. The first level concerns the weekly irrigation bulletins in the main agricultural areas of the island, with the aim of informing farmers and local water managers about crop irrigation needs. The second level concerns an innovative digital web-based platform for the demonstration, for the determination, of the irrigation needs of rich crops at parcel level. And the third level of this approach includes an open source Internet of Things intelligent irrigation system for optimal individual parcel irrigation scheduling. Includes also the corresponding laboratory soil hydraulic characterization service. Regarding the second level of this advisory scheme, the web-based GIS platform, this is a decision-making system that combines several components, as we can see in this figure. First of all, collection of meteorological data and land use parcels. The second component is related to the algorithms for calculation of crop evapotranspiration, taking into account the development stage of the crop as well as the age of the trees. Collection of in situ field measurements of soil composition. Satellite remote sensing techniques in combination with field measurements to depict high resolution and accurate soil texture map for the whole island of Crete. Sustainable cultivation practices for saving water per crop and parcel geomorphology. For instance, deficit irrigation in areas with limited water sources. And of course, the interface of this web-based platform that incorporates all these inputs to an optimal agricultural irrigation plan at farm scale. This platform, named Deficit, is free via the website. Here we can see the link of this platform. Also here we can see the satellite-based base map environment of this platform. The meteorological data that was used in this platform come from 18 meteorological stations, and these stations are well distributed in the whole area of Crete, as we can see in this slide, and especially in agricultural areas, capturing in this way in detail the dynamic climatological conditions of the island. Now, in this figure, we can see the soil texture map from a part of the soil texture map for the island of Crete. This figure depicts the soil texture classification map which was produced using satellite images and field measurements, as well as laboratory analysis. This information is also incorporated within this platform. Here, as we can see, the blue colors represent coarse soil textures, while the red color, for example, represents very fine soils. And here is the web interface where the satellite-based map layer is enabled, where irrigation needs and water conservation practices can be provided for a parcel, identified either manually by clicking directly on the map using the mouse, or by entering coordinates in the search tool, as we can see. Now, regarding the third level of advisory irrigation system and the Internet of Things Smart, Internet of Things Smart system. This system includes soil moisture and atmospheric sensors installed on the field. The user in the environment of this system can select a specific sensor, and they can see straight away all these plots, either in the smartphone or PC, controlling, of course, the needs of their parcels. Based on this information, and in case, for example, that soil moisture is below specific thresholds for the irrigation needs, an alarm message is sent to the farmer to inform about the needs of irrigation and the specific dose that could be applied per tree. A fact of course, that can improve the efficiency of irrigation and save time and effort from the farmer. Also, I have to say that this energy-independent system that provides farmers with specialized information regarding the optimization of the use of irrigation water, saving time and, of course, energy for farmers. Here we can see some indicative results from the application of this holistic irrigation advisory scheme in combination with the previous mentioned good agricultural practices in many olive parcels in the whole island of Crete. Those results demonstrate how this approach can positively affect the quantity and the quality of the production. So specifically, olive production was increased up to 58%, water use efficiency was improved by 39%, and olive oil quality was increased, both in terms of polyphenols and acidity, lower acidity. Furthermore, it is estimated that the above approaches, if implemented by all farmers and crops in Crete, could reduce the carbon footprint by almost 3,000 tons of carbon dioxide on an annual basis due to reductions in the required travel for irrigation. From those two examples, we can obtain several important lessons. First of all, combining solar energy with efficient irrigation technologies leads to strong gains, not only in water saving and energy reduction, but also in olive yields. Moreover, advisory system, digital platforms, and the Internet of Things can tailor irrigation to crop and parcel needs, enhancing olive product in quality and quantity terms. Also, soil practices, when combined with water and energy technologies, multiply the benefits. So together these examples show the power of integrated approaches to overcome the challenges of climate complexity. Of course, there are still barriers to apply the soil, water, crop, energy nexus in practice. The most common barriers are, first of all, the problem of fragmentation. Different agencies often work separately with little coordination. Another challenge is, of course, the cost. Many of these technologies require high initial investment, and of course, small farmers often cannot afford this issue. And finally, also face gaps in data and monitoring approaches. Looking ahead, there are a few clear steps we should take to overcome these barriers. First and foremost, collaboration is required of research teams, which should include soil scientists, hydrologists, energy scientists, economists, and social scientists. Second, farmers and local communities must be directly involved. Their knowledge and experience are essential for designing practical solutions. Third, we need better data and monitor systems that last over time and cover soil, water, crops, and energy together. New tools like remote sensing and Internet of Things system can help, but they must also be simple and affordable. And finally, policies must give the right incentives, supporting sustainable systems instead of isolated practices. To conclude this presentation, agriculture must adapt to climate change by connecting soil, water, crops, and energy in a smarter and more sustainable way. The soil, water, crop, energy nexus is a useful framework for this, but success depends on integration, fairness, and flexibility, and not only on new technologies. Olive farming, for example, needs to be seen as a dynamic system that responds to climate change, not as something fixed. Holistic and inclusive approaches are more likely to succeed. Based on this, the cases from Morocco and Crete show that these integrated solutions can really work, giving us higher yields, better water efficiency, improved olive oil quality, and low energy cost and emissions. So the message is clear. We can create farming systems that are more robust and sustainable for the future if we carefully connect soil, water, crops, and energy components. So thank you very much for your attention, and I am here for any clarification. Thank you.
Thank you very much for this interesting presentation. Unfortunately, we have no time for questions at this moment, perhaps at the end of the session. So we are going to continue with the next speaker.
from the University of Granada. First of all, I acknowledge to Antonio and the UNIO Institute for inviting me to be here. I'm sorry for my English, but I'm not important. The important thing is the hydroinfiltrator. The hydroinfiltrator is a solution for the drought. And I try to explain you. This is a video that we made a long story short. So let's go. No se oye. Tiene sonido, no se oye.
What is the biggest limitation for your cultivation? Water. What happens to rainwater? Runoff? Evaporation? Drought? Is there a solution? Hydroinfiltrator. Composed of ultra-porous material that absorbs up to 5 times its weight in water, promoting the formation of preferred droughts with the plant's roots, through which we achieve permeation and accumulation of water at a considerable depth, preventing evaporation and increasing production. More water equals more harvest. We can also supply nutrients, direct root fertilization. Additionally, with each hydroinfiltrator, we capture CO2, thus caring for our planet. The hydroinfiltrator is also used in irrigation, maximizing water usage, making it ideal for deficient irrigation. Deep watering, direct supply of nutrients to the roots equals higher production. Without the hydroinfiltrator, evaporation and accumulation of salts, less production. Therefore, we want more production with hydroinfiltrator. The hydroinfiltrator is also used in reforestation and gardening. More H2O, more nutrients, more O2 equals greener trees in our world and in our cities.
So, all the time we are talking about this problem. We must face the drought of the soil and even the erosion of the soil and the loss of fertilizer. You can see in this is a video, this is a video, can you put here? You can see the color, okay, thank you. This is, you can see the color of the water. Is proof that the soil is lost too. In this land, we are losing not only soil, we are losing water that is the best of the best quality, and it's free because the rain put the water in the land. Well, when drip irrigation, we lost a lot of water by evaporation. Well, the solution is a nature-based solution. Is the hydroinfiltrate. The solution. The solution that more farmers put in the land is creating a microbasin that collects all the water, all the runoff water, and with the hope that this water infiltrates into the soil. But in the bottom of this microbasin, a crust is formed by the accumulation of clay, and is even less. The infiltration of water is less. Well, this is a solution. The solution that I come here is the hydroinfiltrator. We put the hydroinfiltrator in this microbasin with the hope that all the water, the runoff water, and even the water supplied by the dripper, we store all the water inside in the soil. Well, the hydroinfiltrator, the principal component is biochar. Well, the point is that we connect the offside with all the root system. And the water passes through the hydroinfiltrator thanks to the preferential root pathway. You put the water here, and you can translate the water in the other side of the tree. Well, the preferential pathway is a good thing for the hydroinfiltrator, and it's due to two reasons. The first one is that the root help soil to create a structure, to create porosity. In this part of the soil, when we have root, the voids, we have more voids. The structure is well defined. So we can store here in an olive tree even 2,000 liters of water. This is the first. And so we connect through the pore, through the voids, all the root system. And the preferential pathway also works due to the curious behavior of the root. The root can shrink and can swell when the humidity of the soil changes. So when the root shrinks, we have a highway through this highway, the water pass and connect all the root system. Well, so the idea is that the runoff concentrate here and infiltrate through the hydroinfiltrator and pass through the whole root system. This is amazing when we have a deficit irrigation. When we have a deficit irrigation, all the water is introduced in the deepest zone of the soil and pass through the whole root system. Even we have to fertilize the tree. You put all the fertilizer through the hydroinfiltrator. It's like when we have ill and we put in the vein a device for pass or medication. How can we know that the preferential pathway work? We made an experiment in Baena. We made a tomography of electrical resistivity. From now on, I call it radiograph. We done with it a radiograph of the soil. And this is the radiograph. This is published in Geoderma magazine. We made the radiograph when the soil is dry. We put 300 liters through the hydroinfiltrator, and later we make another radiograph. And you can see the distribution of the water. This is the proof that the preferential pathway works. And the result is that. Without hydroinfiltrator, the harvest is lower. This is in our experimental plot. Well, this slide is from a project. We put a probe. This is a section, of course, near 20 centimeters, near the hydroinfiltrator. This probe takes data of soil humidity, soil water content, and even the temperature, but I analyze the soil water content. This is the control. This is in olive, rain-fed olives. This is the control. This is the control. Sorry, the hydroinfiltrator with a microbiome. This is the period of analysis. And you can see this is the precipitation. You can see that even a small precipitation, this is precipitation, generate runoff, and the runoff can, we register increase of the water content in the deeper zone of the soil. Sorry, this is the soil water content at 10 centimeters, 20 centimeters, 30 centimeters, and so on. But without hydroinfiltrator, the content is the same. But in this month, the rain, the precipitation is about 200 liters square meter. And of course, this water enters the soil. Is normal. But in this case, even a small precipitation, the water reaches the deeper zone of the soil. This is in rain-fed. This is the radiograph of the control before after the period where we have some water. But when we have the hydroinfiltrator, the store of water is higher. And in drip irrigation, it works better. We have three cases. The first one, the control, only a dripper. The second one is the hydroinfiltrator with a dripper. And the third is an hydroinfiltrator with a dripper and a microbiome. This is the best option because we can store we concentrate the runoff and even the water put through the dripper, sorry. You can see this, for example, when we have only the hydroinfiltrator, this rain can affect in deeper zone of the soil. But when we have the microbiome, this rain stored in deeper zone of the soil. This is the radiograph of the control when we have, after this rainy month, we have water. This is, with the dripper, we store more water. And the dripper and the microbiome, more water in the deeper zone of the soil. Well, this is a summary of all of this. The control divided by the microbiome is this 10 centimeters, 20 centimeters, 30, and so on. We store more water when we have the hydroinfiltrator in a microbiome in rain-fed soil, rain-fed olive tree. In drip irrigation, we can see the same. This is for the old period, when the control behaved similar to the dripper hydroinfiltrator. This is analyzing all the period, but when we only analyze the period of irrigation, or drip irrigation, we can see that the control is less than when we have a dripper and when we have a microbizing and a dripper. Well, the hydroinfiltrator not only works for olive tree, works for all kinds of tree, even in the tree of the cities. Thank you very much. If you have any question, please, Dennis. Yeah?
Only one question, please.
How long have you had to keep the hydroinfiltrator in the soil before seeing those effects?
We must put the hydroinfiltrator upstream.
But when?
When? Whenever you want.
No, I mean, how long it has to stay in the soil?
Sorry? All the time, of course. You put this.
¿Cuánto tiempo pasó entre que lo pusiste y hiciste la radiografía?
Eso, la radiografía, del primero. The first one, more or less 7 years. The first one, but the other radiographies, 3-4 months.
For accepting this invitation, the floor is yours.
Thank you very much, Maria Dolores, and I'd like to thank the organizing committee to invite me in this Congress, and also to allow me to present to you my research within the framework of Olive for Value project. Olive for Value is a European project. The coordinator is an ATAC group, is a Spanish company. The project involves 16 partners from 9 European countries. The aim of the project was to valorize the waste from olive oil production, in particular olive leaves, to obtain products with interests in the pharmaceutical, food, feed, and cosmetic application, and reduce the pollution and reduce the waste cost. These are the partners of the project. There are in the project many companies, but also some university of Florence. I come from University of Florence, University of Halle-Wittenberg, and then there is also a colleague from Polytechnic Institute of Braganza. I know that there are many people from Braganza here. The main step of the project was, first of all, a valorization of the leaves, then to obtain leaves with high phytochemical compositions. By refining and then developed different purification processes using green extraction and zero waste approach to obtain extract or biorefined products. Then these matrices are subject to biotransformation from the partners, enzymatic, and also for we can use the extract for encapsulation, for micro and nano-encapsulation, and for formulation. This is part of my work. And the preparation of this formulation is has the aim to obtain a prototype for a product used in the food, pharmaceutical, cosmetic field market. And also there is a partner that check the reliability of the project, the cost, the sustainability. The main results of the project obtained by different partners. The partners developed a methodology for rapid biomass scanning. In particular, our company developed a near-infrared device prototype. NATAC performed the purification of the extract and the biorefined product and isolate about 40 bioproducts of olive leaves. These products are subject to biotechnological processes using enzymatic transformation microorganisms. Also, the product obtained from NATAC as a formulate in micro and nanoformulations. Also, some partners developed a method to obtain a higher purification compounds from the extract produced by NATAC. The extract show a very antioxidant, important antimicrobial activity, then are used again in viral infections in Atlantic salmon aquaculture, show the neuroprotective active, in particular in a model of neurodegenerative disease in nematode, and also has good performance in cosmetic sector, and so on. About my work, this is a different point of view with respect to author communication of today or yesterday, because my group is a phytolab group. I am a pharmaceutical technique, and then I formulate extract or single components obtained by vegetable matrices using all conventional formulation, for example, capsules, syrup, solution, topical formulations, but also, in particular, applying nano drug delivery systems used for synthetic drugs also to natural compounds. Drug delivery systems are many systems that contain liposome, microemulsions, contain complex with cyclodextrin, lipid nanocarrier, these delivery systems have some important characteristics to overcome limits of natural compounds. The main limits of these compounds are solubility in water, stability, and also low permeability across the physiological barrier. With delivery system, in particular nano delivery system, the size of the carrier and also the possibility to functionalize the surface of the carrier help to improve solubility, stability of the loaded drug. The permeability of the drug is possible with drug delivery systems obtain a targeting of action, in particular against cancer cells, then reduce the dose of the drug and also reduce the toxicity of the drug. In the Olive-for-Value project, I prepare different formulations, macro and nano formulations, to implement the solubility of matrices, of the extracts, extract or single compounds, to improve dissolution profile, stability of the molecules. I select the formulations easy to prepare and also for easy possible scale-up, industrial scale-up, and also I have to select excipient, no toxins. I use the excipient used in a pharmaceutical or food field. I prepare different formulations, liquid formulations, in particular macroemulsions and polymeric micelles, and two solid formulations, solid dispersion and co-ground products. The formulations are characterized with different methods, in particular in vitro test to evidence the influence on solubility of the compounds, storage stability test, gastrointestinal stability test. Also, we verify the influence of formulations of intestinal permeability in vitro or with in vitro test, and I performed in vivo, sometime in vivo studies to demonstrate that the formulations improve also the B-efficacy of the compounds isolated from olive leaves. I work with two extracts produced by NATAC and one single compound. In particular, I work a lot with triterpenes because triterpenes are very insoluble compounds in water. Then I work work with pentacyclic triterpenes-enriched extract, TTP70. This extract is enriched extract in triterpenes, about 70%. I work with oleanoic acid, pure oleanoic acid, and an abstract defined OPA40 is a polyphenolic extract with high content of oleuropein. First of all, I developed the microemulsion. Microemulsions is a biphasic systems, contain a water phase, oil phase surfactant. The dimension of inner phase are very small in the nanometer region, and then we have a limpid formulations. By microemulsions, we improved the solubility both of oleanoic acid and triterpenes, because oleanoic acid has a solubility in water less than 1 microgram per milliliter, triterpenes about 7 microgram per milliliter. In this case, with the microemulsions, we obtain a solubility of 1 or 3 milligram per milliliter. And the microemulsions are a very useful tool to formulate extract, because extract contain many compounds with different characteristics. Here, there are the components of the different microemulsions. The components are no toxic excipient, in particular for olive phase and for tenside. And some of these constituents are also substances defined GRACE from FDA. And some of these constituents, for example, transcutol or TPGS, TPGS is a derivative of alpha tocopherol, are penetration enhancers. Then I select excipient also, not toxic, but also to improve the permeability across intestinal barrier to promote the absorption. Macroemulsions can be on the market as a solution, liquid formulations, but also is possible without water, insert the oil phases inside of soft gelatin capsule to obtain a solid formulations. We evaluated the influence of constituents of macroemulsions on the permeability, intestinal permeability of triterpenes and oleanoic acid. First of all, using a very easy test, the PAMPA test. The PAMPA test is a test to study the influence of passive permeability of constituents. There is in PAMPA a donor compartment, an acceptor compartment. In the donor compartment, we put the formulations. In the acceptor compartment, we evaluate the compounds that pass through the membrane. And there is also artificial membrane that contain lecithin and cholesterol, derivatized with lecithin and cholesterol to mimic the intestinal barrier. Oleanoic acid and TPP70 extract are completely impermeable in this test, because the permeability coefficient is very low. In the case of all macroemulsions, we obtain a very good recovery, a very good improved permeability. For example, for this formulation, for one microemulsions containing the extract, triterpenes extract, pentacyclic triterpenes extract, we tested the influence of the extract, but also the microemulsions on accumulation, lipid accumulations in the liver cells. Lipid accumulations is elements that produce tumorigenesis. In the literature, reported that high glucose levels accelerated the tumorigenesis, and oleanoic acid reduced these accumulations. We tested the extract to evidence the effect also the complex matrices on this effect, and also we demonstrated that the macroemulsions, the extract loaded macroemulsions, improved the efficacy of the extract in this action. We performed the serviability test in the presence of high glucose levels in the cells, in the liver cells. We selected the no toxic concentration for the test, and by a colorimetric reaction, we evidenced that in the cells treated with high glucose levels, we have a high lipid accumulation. When we applied the extract, triterpenes extract, we reduced the lipid accumulations in dose-dependent manner. In particular, about 30% of reduction of lipids was obtained. But when we introduce in the cells the extract formulated in microemulsions, we obtain a reduction of 50% of the lipid with a good effect. This is because because the constituents of macroemulsions improve the penetration of triterpenes inside of the cells. No effect was observed for macroemulsions without extract, the control thesis. In the case of OPA40, then a polyphenolic extract, we used the polymeric micelle for ameliorate the solubility, but the extract has a good solubility in water, but also the stability. We used the polymeric micelles. This is a Kourgialas nanostructured colloidal system made by amphiphilic copolymer. We used the polyoxamers. This is a compatible, non-toxic polymers used for human application, also for parenteral application in men, and also TPGS to improve the penetration. We obtain inside the micelles, we insert the extract, not only oleuropein, the main constituents, but the other constituents of the extract. We obtain a nano device, a nano carrier with small size, very homogeneity of the system. Improve solubility, but in particular the stability of oleuropein, and it's also possible to transform this colloidal system, then a liquid formulation in solid formulations by freeze-drying process. The freeze-drying process improve also the stability of the extract. Also, in this case, we evaluated the influence on permeability. In this case, we used Pampa test, but also CACU2 test. CACU2 test is similar to Pampa test, but the membrane is derivatized with cells, in particular CACU2 cells that are cells that developed in intestinal cells with the microvalves. And also in this case, we evaluate here not only the passive permeability, but also the influence of active mechanism of permeability, and also in this case, the apparent permeability coefficient was increased, and good results due to the formulations. Two solid formulations developed in the project. The first is solid dispersion. Solid dispersion is a mixture, dispersion of hydrophobic drug in hydrophilic carrier. We used different carrier, hydrophilic carrier, different method to preparation of this solid dispersion. For example, physical mixture kneading or solvent evaporation method. And we obtained the good results in improvement of solubility, in the case of triterpenes, of course, using polyoxamer 407 or 188, or gamma-cyclodextrin. The solubility was increased also for triterpenes extract. We characterized the solid dispersion with different technique, in particular considering a possible market application with we insert the powder, the solid dispersion, inside a hard gelatin capsules. This is a very easy dosage form, and we performed on this capsule a dissolution test. The dissolution test is a test required by pharmacopoeia for solid dosage form to demonstrate the release from the dosage form of the constituents. For all compounds, oleanoic acid or TTP70, the extract, we observed a very good improvement in dissolution profiles, because this black line are the dissolution profile of the oleanoic acid or triterpenes without formulations. The other line are with formulation in the presence of solid dispersion. We have a very good improvement of 2-3 times of dissolution profile. The last one, solid formulation, is a formulation, solid formulation, then we obtain a powder obtained by mechanochemical activation. Mechanochemical activation is a process that applies to carrier, hydrophilic carrier, coformer, and molecules, a drug, energy. In this case, the energy is represented by ball mill. We insert in the mill oleanoic acid of extract and then a coformer. We have a good result with the sodium cholate. We co-milling and we obtain a powder. In this process, we have a coamorphization of the drug of the extract, by, in particular of linoleic acid, demonstrated also by team analysis. Also, we have interaction between carrier and drug, and we have obtained a good improved solubility for both matrices, so linoleic acid and the extract, and also improved a good improve in dissolution profile of compounds. We tested, in this case, I report in vivo test, in vivo study performed with my colleague pharmacologist in University of Florence, where we administered the co-ground product of linoleic acid and sodium cholate in a rat model of colites. And we observed that the co-ground significantly reduced the pain, the visceral pain associated to colites with respect to unformulated linoleic acid. It is approved also not only of improved solubility and permeability, but also bioavailability of the compounds due to the formulations. We can observe that we have good results of the pain in the animal using linoleic acid 30 milligram per kilo, and using co-ground product, we have best results in the dose of 30 milligram per kilo. 30 milligram per kilo, the co-ground is a product that contain 1-to-1 in weight coformer linoleic acid. Then co-ground contain 15 milligram of linoleic acid, and then we have the good effect, similar effect, then 30 milligram of linoleic acid. Then we reduce an half the dose active in the animal. Linoleic acid at 15 milligram per kiloliter is not active, then, and is not effective. It is proved the efficacy of the formulation. The last part, the final part of my work in the project was the prepare composite formulations. Then use the formulation developed, optimized for triterpenes, mix 3 formulations with OPA 40, and then study the solubility and dissolution profile. We obtain very good results with respect to a mixture that contain only extract without formulations. We have improved solubility of both constituents, dissolution profile, and also stability. Then I concluded my work, and with these results, I show you that the nanoformulations or microformulations can improve the biopharmaceutical characteristic of extract. Extracts are complex matrices to formulate, and also single compounds, can improve the dissolution profile. The formulations can improve also the bioefficacy of the compounds as proved by in vitro and in vivo test. And also we have also optimized composite formulations to produce a product for possible market applications that contain both constituents with good characteristic, biopharmaceutical characteristic. I would like to thank all people that collaborated with me in this project, from University of Florence, but also from University of Halle-Wittenberg, from NATAC, some research of NATAC, and thank you for your attention.
Thank you very much for your presentation. Congratulations for the results of the project. I'm very sorry, but we have no time for questions.
Thanks. So yes, so today I'm going to be talking about the results of the F-COMP project, where we valorized olive pomace for energy in particular. So the concept of this F-COMP project is we wanted to convert low-quality biogenic residues into fuel, into solid fuel. And we focused on wet residue streams because they're so challenging. There's a lot of energy in wet lignocellulosic and sludge residues in Europe and all over the world, but they're very difficult to handle and to treat because of their high water content. So we employed a hydrothermal conversion, so we didn't have to do any pre-drying to convert the wet residues into solid fuels. And the reason why this is important is because as we move towards a renewable energy system, so in the Netherlands and across Europe, we're moving more towards wind and solar, especially wind in the Netherlands. And sometimes that power can be intermittent. So the idea is that we have these intermediate bioenergy carriers, or these solid fuels, to help offset some of the fluctuations in the grid power. So this is the process. We didn't just use olive pomace, but that's what I'll focus on today as a feedstock. We also use paper sludge, so from a paper mill wastewater treatment plant, and orange peels. The hydrothermal process is a patented process developed at TNO. It's called torwash. Basically what goes in comes out, but it's more easy to be dewatered and compressed. So then we do a mechanical dewatering to have a solid fraction, which is basically our solid fuel, and also a liquid fraction, and that can be digested to produce energy in the form of biogas. Also from both fractions, for each of the feedstocks, we also checked to see if we could do some nutrient recovery. So the main objective was to really validate this at TRL 5 in the locations where the residues were produced, doing pilot testing continuously, processing these residues for a long duration, so for several days or weeks. And then we wanted to produce high quality solid fuels. So first we had to kind of optimize everything. So we started from screening tests at a very small volume of about 100 milliliters. Then we did larger tests in autoclaves. And then we have this mobile pilot plant. It's in a container. You can see it on the right. And that runs continuously at around maximum 50 kilograms per hour. And we can take it on the road with us. For these studies, we ran it at around 25 to 30 kilograms per hour. And our target parameter, what we really wanted to optimize, was the dewaterability of the material. So we took our pilot plants on a whole European tour in this project. It was really fun. So we were in a paper plant up in northern Sweden. We were in Spain also for the orange peels. And then for the olive mill waste, we were in the south of Italy. So this is what it looked like at the olive mill. Some nice pictures here for you. So this is the olive mill location. We were there during the time when they were harvesting olives. So there were all these big piles of olives around ready to be processed. And in the mill, the olives went through a cold press. And the material that we received was the olive pomace. So this is the material after the first oil extraction. And then there was also a process to remove the remaining pieces of the pits from the olive. And then everything that was left, that's what we received as input for our process. So that's what I'm calling olive pomace in this project. This is what it looked like on site, just to give you a bit of perspective for pilot testing. We had 2 shipping containers. So one was where the actual reactor was located. And then for safety reasons, because it's under pressure and it's hot, we can't be in there. So then we have a control room where we can sit, we can do we had a small lab in there, and we can monitor the process. Everything is fed through these IBC tanks, a 1 cubic meter IBC tank, and then the product also comes into an IBC tank. We also have some sampling points. So I wouldn't say it's a large pilot, but it is, it is representative, I would say, of what you can do at a larger scale, and it is operated continuously. So here's some pictures from the olive pomace. So you already saw the top left. That is the feed that goes in. And then at the bottom, you can see this is what comes out on the bottom left. This is what comes out of the torwash reactor. So you see the solids are already separating very nicely from the liquid fraction. That's a good indication that when you compress it, you'll dewater it easily. You can also see some of the green. That's residual oil. So there is still quite a lot of oil left in the olive pomace, and in the filtrate after dewatering on the bottom right, there was this layer of oil on top of the filtrate. And you can see the solids as well. So it dewatered really nicely. We had these really beautiful solid cakes. And then we tried to pelletize them, and we could make pellets, but the pellets were quite powdery. They broke apart very easily, and that's also because of the residual oil in the material. So in general, this is the effect of the FQ process on olive pomace residue, but also on other feedstocks. So basically, in the solids, we get higher dry matter. That's great if we're going for a fuel. We reduce the ash content. The carbon content of the solids increases, also very good for fuel. We don't see a ton of change in nitrogen or hydrogen. And the higher heating value, which of course is very important for a fuel, so how much energy is located, or how much energy is in those solids, increases with this F-cubed process. So that's great from the perspective of making a solid fuel. We also see some interesting things with how elements partition in the process. So after we do the Torwash hydrothermal treatment, certain elements favor the solid fraction and other elements in the liquid fraction. And what we see is that a lot of the salts, so chlorine, potassium, and sodium, really get washed out with the liquid fraction into and out of the solids. And that's also very, very good from a fuel perspective. You don't want those salts in your solid fuel. They can cause problems when you then combust the solids. Metals tend to stay in the solids, which is not usually a problem for most feedstocks. So this is for olive pomace, so you can see what goes in and what comes out, and you can see the increase in dry matter content. You can see the ash is washed out as well, and also this increase in higher heating value from 23 megajoules per kilogram to 29. So that's also very good. We also important from a waste management perspective is we really reduce a lot of the moisture in the waste stream and the volume. So this is also really important for example, for disposal of the waste and for costs. These are the pellets. I included the pellets for olive and orange. This is from a publication. And basically, this is just showing the quality of the pellets that we were able to produce and comparing it to a wood pellet standard and a biomass pellet standard. And what you can see for olive and also for orange is that we come very, very close to meeting the standards for even a wood pellet and also a biomass pellet. The only thing where we are a little bit off is there's a bit too much sulfur and a bit too much nitrogen in the olive pellets. And I do think that with more optimization of the process, you could address that and you could create a solid fuel pellet that meets the wood pellet standards. So that's also a great result. Of course, when you go to pilot testing from lab scale, you always have problems. So we encountered quite a few issues, let's say. We had to really optimize dewatering. We were seeing differences when we pressed things. So sometimes maybe the pressure or the timing wasn't quite right, and we would end up with solids that were still quite wet and quite muddy. With the olives, even though the pomace had gone through a process before to remove the pits, there were still a lot of olive stones, pits, which you can see in the pictures here in the material that we received. And that created a lot of problems in the beginning in our reactor. They would just settle in the reactor and burn to the edge of the reactor. So we had to we ended up adding in another step to sieve out the olive stones before we put the pomace into the reactor. As I said, also the pellets were very powdery. So initial durability tests were quite good, but then when we shipped them anywhere, like for combustion testing, what we saw is they would just break apart, and with any kind of movement, they would break apart. And so this is because of the residual oil in the pellets. So that's also something to consider if you want to sell the pellets or ship the pellets somewhere, or if you really need pellets to feed into your system. This might be a problem if you don't do some oil recovery first. We did, in the project, combust the pellets to produce energy. So all the solids, even the olive, it could be pelletized. The standards are really good, as I said. we produced a lot of syngas in the combustion, especially from the olive pomace, because again of the oil. So they produce a lot of energy. Actually, there was actually a small explosion when they first did the olive pellets, and they blew the lid off of the stack of the combustion chamber. So a lot of energy produced from the olive pomace pellets, but that's because of the oil. We could also recover some nutrients from the liquid fraction. From the liquid fraction, we also did some anaerobic tests to see how much biogas we could produce. So basically, in the olive pomace, we could see quite a lot of biodegradability, and the organics could be converted to biogas. And based on the economics, basically it's worth it to also valorize this liquid fraction based on the biogas that you would get. When we did some economic and value chain considerations, just to be transparent, there really isn't yet a clear business case for the olive pomace. So even though the pellets are really good, the process worked really well, we could recover nutrients, biogas, solid fuel, even some of that residual oil, even though it's a low quality, the business case is still not there, and that's because it is a seasonal feedstock. And so when you size the equipment for the amount of pomace that's coming in to treat it all, your capital costs are very high, and then you're only using the equipment for the olive season, which is quite short in the grand scheme of things. So you need to, if you want to improve the business case, you really need to have more operational hours. So that means processing other residues or storing the residues to process them throughout the year. So to summarize, we did hydrothermal treatment of olive pomace to produce energy. So that's both solid fuel, but also biogas. And it was really promising from an environmental point of view, and also from a waste management perspective. So the process worked very well for this waste stream. But the business case is still difficult. And that, in this project anyways, was because of how we estimated the cost, and it's due to the seasonal nature of the feedstock, and then the equipment costs are quite high. The fuel pellets that we produced are close to the quality standards of wood pellets and biomass pellets, so that's great. And you do need to still do some additional optimization of the process and equipment. So again, as I said, related to sizing and operational hours, that's recommended. And if you can do that, then I think there's a nice opportunity here to valorize this waste stream. So thank you very much. There's my email address there. You can also Google the F-Cubed project and see if you want to read more about everything that we did. Of course, this is just a small piece of it. Yeah, and I will be happy to answer some questions.
My name is Jesús Castillo. I am R&D project manager at Andaltech, a plastic technological center located a few kilometers from here. I am going to present LIFE-COMP0LIVE Project in this Congress. Firstly, we will make a brief description of the project. Then we will speak more in detail about the technical part. And at the end, we will present some future work after the result of the project. So let's start with a brief description. Here, what we made is a new generation of biocomposite based on olive fiber from industrial application. So we make a valorization of olive tree pruning waste, and we transport that in biocomposite for different industry, automotive and furniture. So the main benefits are to avoid the burning waste in field, as well as to substitute fossil-based raw material. Here you see on the left a picture of olive tree field that you see a lot in that area. The pruning that we obtain all year from that farming, and the final part that we obtain with our biocomposite made of olive tree pruning. Here, a scheme of the process. On top, a more schematic one, and below, a real picture of the process. On the left, we have the fiber that we use for the biocomposite. In middle, the recyclable polymer matrix. It's important to say that it's recyclable also, the polymer matrix. And finally, some part that we manufacture with this kind of biocomposite. And on top, you see the fiber with a random orientation depending on the injection direction, so depending on the shape of the part. It is a European project led by Andaltec, and all the partners are from Europe, mainly Spain, France, and Germany. Specifically, we have been working with FOR, Plasturgia, Caliplas, Matricería Peña, University of Jaén, and Citoliva. Here, a summary, a flowchart of this project with different actions, five main actions. The first one is about the olive tree pruning. Firstly, we make the collection after the pruning of the trees made by the farming. Then we transport and storage in our facilities in order to, in another step, work with our biocomposite. We make a fiber treatment, a compounding, scale-up, and characterization in order to validate the properties of this material for industrial application. And then we make the manufacturing of real prototype for real industrial application. And so in that sense, we make a full validation of the material. And finally, thinking on the market, we make replicability and transferability tags. So now let's move more in detail about the technical part for this project. The first step, like we said, is the collection and conditioning of the olive tree pruning. We need to separate leaves because this material is not useful for our application. So only the fiber is what we need. Then we make the milling in a scale-up milling. And after that, we make the sieving in order to take only the proper sizes of the fiber that we need, because it is, I will say, some of the most important part, to take only the exact sizes, not a lower one, because decrease maybe a lot the properties, and a bigger one is not possible to be manufactured with the current technology of plastic processes. And also another important step, I will say, is the chemical treatment, because if you mix only the fiber with the polymer matrix without any chemical treatment, the bonding or the joining is not strong, so the mechanical properties at the end will be weak. So it is another key point of the project, achieve a good chemical treatment for the mechanical properties at the end of the material. When we have made the chemical treatment, the next step is to mix the olive tree fiber with the polymer matrix. For the pilot scale process, we use this little mixer, this little equipment, in order to obtain, after the cooling, little block of the biocomposite, which in another step we mill and sieve in order to take the raw material, so the final biocomposite, that we use for, in another step, thanks to an injection machine, a conventional injection machine and conventional injection mold, manufacture some sample for the characterization. Here on the right below, you see some picture for the sample made for tensile, flexion, or impact stresses. And that makes possible to the characterization of the biocomposite in that pilot scale. So then, after this characterization, we move to another step, is the characterization thinking for industrial applications, so with more amount of material. So for that, we use bigger machine. It's the strategy to use bigger machine, like bigger tractor, bigger equipment of storage. For the milling, previously we used this little one machine, and for this industrial escalation, we use equipment with around 160 kilograms per hour for the milling, and for the sieving, around between 300 and 400 kilograms per hour equipment. Also, the chemical treatment, we use different equipment. In that case, a reactor with 50-liter capacity, generating a production of treated fiber per day around 10 kilograms. In total, we obtain 350 kilograms of treated fibers successfully. On the left, you see the untreated fiber and how it looked. And on the right, the treated fiber with the different looks after the chemical treatment. For the compounding, in that case, we use a continuous process with a twin extruder. It is an automatic process in which you add separately the fiber and the polymer matrix. Then we have a continuous extruder that mix the two material and make the biocomposite, and then automatically it is coated. We make, in that case, 800 kilograms of biocomposite with different properties for the different end users, the different supplier of this material. In this case, Ford, Plasturgia or Caliplas, and Matricería Peña. Here, I show you some real part manufactured with this biocomposite. In fact, I have someone here. For example, it is a profile made by extrusion. And we use that for manufacturing this kind of equipment, a bench, a seat that you can find in a garden or in whatever place. Also some part from the automotive sector. Some real part that you can find in your car, like this one. It is for Ford. Or a bigger one that you can find in the back of your car. You see also the fiber inside of the material, that apart of being a sustainable material, I think is a good material in terms of appearance. So about the future work, after the result of this project, a lot of R&D line appear. So let's speak about some of them. In fact, some of them are still working. We are working right now in that, and other it is planning for the future. So, for example, obtaining cellulose acetate or obtaining nanocellulose from the olive fiber, as well as optimizing the chemical treatment. It is maybe the weak point at this moment. We need to improve that in terms of cost and environmental impact reduction. Also use the lignin contained in the olive tree pruning, as well as use this fiber for textile purpose, for the textile industry. Also use this biocomposite for other manufacturing processes like additive manufacturing or packaging with thermoforming. Develop mathematical model for predicting the aging degradation of this kind of biocomposite. Study the recycle cycle that this material is able to achieve at the end of their life. Develop optimal revalorization strategy for the part made with this kind of biocomposite, and also apply the same strategy to other agricultural or industrial or forestry waste. Also, an important idea is, or an important point is, we are planning to set up a startup. So we have a business plan for this kind of material that we have developed. The business idea is to manufacture customized biocomposite based on green polymeric matrix and natural fiber on demand for different industry, for different sector. And the competitivity advantage of this idea is summarized here. We have different competitivity advantage. The first one is that we don't need to cultivate more crops. With the current one that we have in that area is totally enough. As you see, we have in that area a lot of olive tree. Few manufacturers know how to mill this material and how to make that. Only us know to do this. The biocomposite cost is similar to that of other polymer. We don't need different equipment that the standard one for the polymer processes. We can manufacture a custom design depending on the necessity of each client. So different biocomposite can manufacture for any application. Also, an important point is that due to the huge amount of olive tree that we have here, we could manufacture the global biocomposite market with this kind of material. So it is all. Thank you very much for your attention. And if you have any question, do not hesitate to contact all of us.
And congratulations for the result of the project. Now I think we have some time for questions. So if there is any question for any of the speakers.